Hi, my name is Haris Jalani and this is my Lab 2 video report. In this lab I analyzed the motion and position change of a falling object that moved with a net force not equal to 0. This meant that the object experienced an acceleration. The object that I chose was a crumpled up piece of paper. Some relevant information for this lab was Newton's first and second laws, as well as the formulas for gravity and drag force. I recorded this by dropping the ball from my hand and recording its motion as it fell from my hand to the floor. A summary of the results is that the ball moved at a non-constant velocity that had an acceleration in the negative y direction. This acceleration was close to but not equal to the acceleration of gravity, which is negative 9.8 meters per second squared. I believe this was primarily due to the drag force and caused deviation between the recorded position time graph and the modeled position time graph, which had no drag force. To improve my results, I could have chosen a more uniform object, such as a rubber ball, because the paper ball that I chose had lots of folds and creases, which increased the surface area and may have increased the drag force. These results are relevant because they help us model real-life interactions with falling objects. Unless you're in a vacuum, objects are going to have more than just the force of gravity acting on them, and being able to model these falling objects helps us in real-life situations. Here you can see the Tracker app, where I analyzed the motion of the falling piece of paper. I set it up so that the x-axis was approximately along the top of my arm, meaning that both the initial position of the falling piece of paper and the entirety of its motion were in the negative y direction. Here you can see its motion. To the right, you can see the y position graphed against the time, both in a graph and a table form. I calculated that the acceleration was approximately 9.281 meters per second squared in the negative y direction. As you can see, this is similar to the acceleration from gravity, but it is slightly less. Here you can see a GlowScript program which approximates the motion of the ball without accounting for the drag force, meaning that the only force acting on the object is the force of gravity. Gravity is set to be 9.8, the ball mass is set to be 4.5, which is approximately the mass of a single sheet of paper. J hat is set as 0.10 since all forces that I'm accounting for are in the y direction. And T is set to be 0.567 because that's the length of the video that I recorded. As you can see, this motion, while similar to that of the one from the Tracker app, has the ball falling slightly faster than it does in real life. Here you can see a second GlowScript program which models the motion of the falling object using both the drag and gravitational forces, overall giving a much more accurate result. I modeled the force of drag using the proportionality constant, also known as B, which I found through trial and error. Here I have it set as 1.889, which is the value that gives an output closest to my measured values. I calculated drag by using this proportionality constant, multiplying it by the speed, or the absolute value of the velocity of the ball, squared, and then pointing that in the direction of the ball's motion, positive or negative. F net is the force of gravity added to this force of drag. Here you can see, through this model, this is much closer and a much more accurate representation. Here we can see all three models graphed on one Excel graph with the raw data to the left. We can see that the model with drag data is much closer to the realistic tracker data, meaning that it is a more accurate representation of the motion of the object. Below, we can see some relevant equations, including Newton's first and second laws, which relate the ways that the gravitational and drag forces affect the object, as well as the formula for final position, which helps us analyze the motion of the object due to the acceleration from the net force. Although neither model explicitly shows the object reaching terminal velocity, the model that has the object with drag force predicts a terminal velocity if it had been allowed to continue, meaning if the object had continued to fall. This is because the drag force is proportional to the square of the object's speed. This deceleration from the drag force is greater than the equivalent acceleration from the gravitational force, meaning that the overall acceleration was decreasing. Eventually, these two forces would have canceled out, meaning that the object would have reached a terminal velocity with zero acceleration and a constant velocity downwards. This net force would have then become zero. If the object was initially thrown downwards, meaning that it had an initial downwards velocity, its terminal velocity would still be the same because the properties of the object, such as its weight, mass, and surface area, remain the same. However, it would likely reach this terminal velocity more quickly. As you can see in this computer model, where I set the initial velocity to be negative 20 meters per second in the y direction, it levels off more quickly, meaning that the force of drag cancels out the force of acceleration more quickly and it reaches a constant terminal velocity. This is because drag is proportional to speed, so if there's a greater initial speed, that means there's going to be a greater initial drag force and thus cancel out the force of gravity more quickly.